Hi everybody, this is Matt and Cole talking about hydrostatic pressure today. In layman's terms, hydrostatic pressure, and I hope cursive is good for everybody. Hydrostatic pressure is the pressure that a fluid exerts upon an object that is inside of that fluid. So let's say you're in your bathtub at home and you're sitting there and you're enjoying yourself and the water's over here, right? And you're underneath this water. This water is actually exerting a pressure upon you, upon your body, from all different directions. And where this pressure comes from is water is a fluid, right? So you have this fluid water. It's red water. And the water is made up of these little molecules that are running around and moving with regards to each other, right? Moving next to each other, around each other, moving in different directions. And so when a force is exerted upon the water, which is the force of gravity upon the water that's like up here, right? This water wants to go down, and so it's got to shove the water down here in a different direction. Where's that water got to go? It's got to go some other direction to get out of the water's way. If you have an object in the way of that water, so like this box that's arbitrarily underneath this water, right? If you have an object in the way, this water molecule here that I'm circling is going to exert a pressure upon this box because it's trying to move into the box. And that force that it exerts on the box is called hydrostatic pressure. Simple enough, right? So hydrostatic pressure, that's hydrostatic pressure in a nutshell. Now, why is hydrostatic pressure important? Well, we have a large amount of water on this earth, and there are a large number of species of organisms and resources that we can find underneath the ocean's surface. So in the Pacific, for example, we have all these gigantic fuel rigs which pump drills way into the ground to get to oil reserves, right? Well, these fuel rigs have to be made of material, and these drills have to be made of material that can withstand the hydrostatic pressure that is exerted upon them by the water around them. And this hydrostatic pressure only increases with depth. And so as you go down, as you go up in depth, which is to say, that's kind of a strange way to put it, but as you increase your depth, you also increase your hydrostatic pressure, which we're going to note with the force with this FP symbol, F sub P symbol. And so that's really important. And when you're creating submarines also, so there's a little submarine here, right? He's an exploratory sub. He's trying to find new species at the bottom of the Marianas Trench. Imagine this was a lot deeper than this picture actually exhibits. This submarine has to withstand the pressure that the water exerts around it, otherwise it crumbles up into a little ball. And whoever's inside of it or whatever material is inside of it, so you take measurements, is going to be destroyed and you're going to lose all that. And that's an expensive loss. So being able to calculate hydrostatic pressure is an incredibly important thing. We'll get into a few other examples as we go along. Other examples include dams. We'll talk about how we calculate hydrostatic pressure in a dam and so forth. But first I wanted to talk about some of the basics of this calculation. So when you're calculating hydrostatic pressure, you're concerned mainly with three variables. First is rho, the fluid density. That didn't come out right. Let's try that again. I went in a highlighter. Rho, the fluid density. Rho is a Greek letter, and we're using it to note, to talk about fluid density. Fluid density is effectively just the number of molecules and the mass of the fluid within a certain space, right? So, for example, water generally has a fluid density somewhere around 1,000 kilograms per meters cubed. And we generally use kilograms as the standard unit for mass and meters as the standard unit for distance, and meters cubed denotes a certain volume because, as we all know, a cube, this is a very badly drawn cube, but bear with me. Within this cube, we're saying that there's 1,000 kilograms of mass if you were doing this underneath some water, right? So that's rho. The next thing you want to be concerned about is volume. As we talked about volume, right? You want to be concerned with the volume that's on top of an object. So if you're underneath the water, like this cube is, you're worried about the volume that is in this area, right? So like in this spot above the cube, so in this cube above the cube, right? So between the cube and the water's surface. And that volume should be generally be talked about in terms of meters cubed. Finally, we want to be concerned with gravity. Gravity is just a constant. You don't really have to worry about it too much. We're going to assume for the most part we're working on Earth and we're not working on Mars. So the gravitational constant on Earth, near Earth's surface, is 9.8 meters per second squared, or thereabouts. And we're assuming that even though you're going to go down to the depths of the Marianas Trench, we're not going to change that gravitational constant for our calculations in order to simplify things. So those are the constants that you have to worry about. We'll give you the formula and how they work out later. First, I want to make some assumptions and clear up some assumptions that we're making as a part of this. So, first assumption, we're doing this on Earth. As I said, the Earth's gravitational constant only applies on Earth. Second, we're assuming that some cataclysmic thing happened and Earth lost all its atmosphere. Or, at the very least, we're ignoring whatever atmosphere Earth has, because adding the atmosphere actually adds effectively a weight on top of the water, so it increases the pressure, and we're not really wanting to account for that right now. 3, we're assuming the object and the fluid it's in is static. So the circumstances are static. If the fluid is not static, then you have a change in the density of the water, for example, above the object. And if the fluid's density is changing perpetually, you can't really make a solid calculation. You can basically only calculate it at an instant in time. And yeah, and while during that instant, at the very least, we want to make sure, we want to pretend that the fluid is static. Similarly, the object, if it's changing its geometric dimensions in the water, then that changes the calculations you're doing. So for example, let's say again you have a cube. And your cube is in the water, and this surface of the cube that I'm shading out right now is parallel to the water surface, right? So the two are parallel with each other. If the dimensions of the cube changed, and this was the water surface, and then this is the cube, then suddenly the amount of water that's above this part of the cube versus this part of the cube changes, and that changes your calculation significantly. So we're assuming that the object is static. We're also assuming that the fluid is homogeneous. Obviously, if you had water and oil above the cube, then your calculations would be different. You'd have to calculate make a calculation for the oil above the cube and also the water and the effect on each other, and that gets really complicated, so we're not going to worry about that. And we're also not going to worry about odd shapes. So going back to the example of you in your bathtub, if you're sitting in your bathtub and you want to calculate how the hydrostatic pressure affects you, you're going to have to start doing things like, oh, well, my leg can be counted as like a cylinder, and my thigh can be counted as a cylinder, and my knee can be counted as a sphere, and we're not going to worry about that, is essentially what I'm saying. We're not going to worry about odd polygons or strange geometries and the like. Good stuff. So, with those cleared up, we're now going to talk about some examples.